Hi everybody, Mr. Kolakowski again. I hope you're doing well. The purpose of this video is to review the circuits lab that you guys did. And if you don't recall, this experiment was done over the course of a couple of days, and this was after we'd gone over the circuit rules. So for example, that was Kirchhoff's junction rule. That was the loop rule. We talked a little bit about how resistors and light bulbs are supposed to behave in series and parallel. So the purpose of this experiment was to sort of see how those circuit rules play out with actual data. Let's go through the experiment. And of course, if you have any questions, let me know. The purpose, again, is for you to kind of get a refresher on what your circuits lab was all about and to sort of see how it applies to the unit, I guess, in its totality here with things like voltage and series and parallel circuit systems. Let's go ahead and get started. So the first circuit that you built looked like this on the table. Your batteries were in a slightly different cradle, but really you have two 1.5 volt batteries connected in series for a total of about 3 volts um, for new batteries. The circuit schematic looks like this. So here we have the symbol for battery, the positive negative terminal of two batteries. We have a switch, it's like a drawbridge that's down, and we have a single loop of electricity going through two light bulbs. If you see a symbol like this in a circuit schematic, that means ammeter. If you see a circuit symbol like this, that means voltmeter. Ammeters are designed to be used in series with circuit components like batteries and light bulbs. Voltmeters are designed to be used in parallel with circuit components like light bulbs and batteries. Okay, so the first thing you did was you tested the gate, the switch, and in this particular case, the flow of the current stopped, and you're not going to have any light turning on. That's because you have effectively destroyed the pathway for the electrons to flow through the loop of electricity. The next thing that you did was you put the ammeter, you set your multimeter to measure as an ammeter, and you placed it at different positions. So you put it at position 1, 2, 3, and 4. And I don't know if you guys recall, but what you found was the current was the same at all of those different positions. This makes sense because if you have a single loop of electricity, all of your electricity has to flow through one solitary pathway, and everything is going to have the same current. The battery, light bulb 1, light bulb 2, all of those different circuit components feel about 0.25 or zero point 0.3 amps. And that's what the answer says here. The current is the same for all devices. Now, in the next experiment, you have the same circuit with these two batteries, switch, and light bulbs in a single loop. But what you were asked to do um, was to place, switching the multimeter settings over so that it would measure voltage drops. You were asked to measure the voltage at different places here. We have A, B, C, D, E, F, G, H. So for example, you put the voltmeter across AH. As you can see here, I found it to be 2.7 volts for the batteries I was using. You put the volt meter across AB, CD, DE, FG, etc. From here, actually, without getting into my data uh, table just yet, you can see that I measured about 1.3 volts across light bulb 1 and 1.3 volts across light bulb 2. That data actually made a lot of sense because if I was getting about 2.7 volts out of the battery, I would predict the sum of the voltage drops here would equal about 2.7. Now you could say, well, how come 1.3 plus 1.3 equals 2.6 volts? You were with a battery system that had 2.7 volts across it. Well, there's a little bit of voltage drop in the wires themselves. The wires are not perfect conductors of electricity. Copper is great, but it's not perfect. You'll see that here in the data. One of these, well, let's take a look at the data and quickly assess what the result was. First thing it says, voltmeters must always be connected in parallel. That's because voltmeters are designed to have extremely high, nearly infinite resistance. Your goal is to not allow the electrons to flow through the voltmeter, and you want the electrons to flow through the circuit as it's built. The goal is to find out how much energy per charge is taking place at the position that you're testing. So from this data, you can see that I measured about 2.7 volts. You guys would have had anywhere between 2 to 3 volts for your data. If your batteries were a little bit older at your table, maybe it was 2.2 volts. If your batteries were brand new, you would have been a little bit higher than 2.7 volts potentially. None of our batteries were brand new. So here, 2.7 volts is about what you would have seen. And you can notice I'm measuring the voltage drops at the two light bulbs. The question here, were you right? Well, my prediction was I wanted to see the sum of the voltage drops be 2.7. I found it to be 2.6. What accounts for that 0.1 volt difference would be the resistance in the wires themselves. So if you were to write that out as a general statement, the voltage drops across light bulb 1 and light bulb 2 added together equals the total voltage drop across the battery. In other words, you're sort of seeing the loop rule in data form. Does 1.3 plus 1.3 equaling 2.6 volts approximately add up to what was provided out of the battery? Yes, it does. This is where the experiment changed a lot. In the next part of the lab, you built this. This is what it would have looked like on your table. Again, the cradles looked a little bit different, but this is the same thing. You have two batteries in series here for a total of around 3 volts theoretically, and here you have a junction. So Kirchhoff's junction rule says that the current, when it reaches a junction, will divide so that if you had 1 amp coming in to the junction and you had equal resistance across both of these resistors, you would have about 0.5 amps and 0.5 amps going through each of the resistors. In this particular experiment, you can see I was measuring 0.6 amps in the loop, the main loop I'll call it, where the batteries are positioned, and only 0.3 amps through the other two pathways. Again, this is because of Kirchhoff's junction rule, which says current will subdivide when you have circuit components in parallel like this. And then, of course, my predictions aren't as important as the data themselves. 0.3 and 0.3 equaling 0.6 was exactly what I wanted to see. What does it say here? Number 7. Label your current values on your circuit schematic above. Locate a point position where it looks like the current is splitting up into two branches. This is called a junction. Label this junction A. Label the other position junction B. Okay, so if we come back over here, you can see junction A, junction B. And one thing I'll say, there is a concept called conventional current. Conventional current imagines that you're following the charge, the positive charge flow. That would be, in this case, clockwise. Actual electron flow is opposite to this, and it would be going counterclockwise in the schematic. And conventional current is the standard, but electron flow is what actually is taking place here in the circuit. If I was really going to look at the electron flow, I would say that at junction B, half of the electrons take first path, the other half of the electrons take the second path. Again, re-meeting up to give this segment of the circuit 0.6 amps all the way through this part that you can see me tracing with my little I don't know if you guys can see that. I'll find out in a little bit, but I do have my little cursor here, and we'll see if that shows up on the video in just a little bit. Okay, so there we go. The junction rule is verified and current is conserved. Okay, now this is a little bit hard with the data to remember where all of these different positions are displayed in the diagram, but we have A, B, C, D, E, F, and then G, H. We'll say A through F is the main loop of electricity, and then if you went A, B, G, H, E, F, that would be a secondary loop. What's interesting though is that, as we'll see in a few seconds, both of those loops can act independently of one another. So there's my schematic diagram. Um, Now, in terms of the data, the predictions are one thing. It's really the measurements that have the value. In this case, maybe I changed tables, maybe I was using a different setup, but I measured the voltage drop across the batteries to be 2.4 volts. 2.4 volts. And so that's from A to F. Now, when I measured the voltage drop across C, D, and GH, I found that to be 2.3 and 2.2 volts respectively. So in theory, if this is 2.4 volts across the batteries, I should get a 2.4 voltage drop across the first bulb and the second bulb. Why didn't it work out that way with my data? Again, resistance in the wires. There's a little bit of voltage drop taking place inside the wires themselves. You can see that right here. 0.006 volts, 0.01 volts, 0.02 volts. These are very, very, very small voltage drops, especially when compared to 2.3 volts. The wires caused some energy to be quote unquote lost in terms of getting from the battery to the individual light bulbs. Okay, speeding up just a little bit here, putting in the switch at points A and B, close the switch, then open it, what happens to the bulbs? Put the switch between B and G, close it, and then open it, what happens? So effectively, if you put your switch right between A and B, you would notice both light bulbs go off when you raise the switch. You effectively stop the flow of electricity to both light bulbs. But if you put the switch between B and G, you're only going to stop the electricity flowing in that secondary loop. The first light bulb is unaffected. This is going to tie in with the next question, which says, with the switch closed, unscrew one of the light bulbs. Do both light bulbs go out? Only one light bulb goes out. And that's because if you were to unscrew light bulb 1, you still have a loop of electricity between the battery and the outside light bulb number 2. If you unscrew light bulb number 2, light bulb number 1 stays on. And that's because, again, you still have a loop of electricity getting back from the battery through the light bulbs. Okay, so let's finish this up. Houses have several circuits in them, usually many more than several. So for example, in my kitchen, I have a couple of different circuits. One of them is for the microwave. The other circuit goes to the refrigerator. Anyway, the idea is you have many different circuits in your home. It says here typically for different areas of the house. So each bedroom, bathrooms, kitchen. And each circuit has several components. So you might have different outlets connected to that same circuit, lights, appliances in your kitchen. Do you think these circuits are wired in series or parallel, and why? Well, the answer is we wire our homes up when you add appliances to a circuit in parallel. It's the convenience of having one device 100% independent from the others. In other words, if your lamp is turned off, you can still turn on the other lamp in the room. And that's because in parallel, you still have a pathway of electricity into the voltage source, which is 120 volts in the home. The one disadvantage I will say about this, okay, if we go back to this picture right here, if I were to keep adding more and more branches to this circuit, you would start to reduce the overall resistance on the battery, in turn raising the current. That's going to make the wires hot, creating the potential for a fire in an extreme case. If we go back to a circuit in series, well, one light bulb is not plugged in or turned off, everything's turned off. Total resistance increases, you have less current. This is a safer circuit. So uh, advantages and disadvantages. Our homes are wired for convenience, and we use parallel circuitry because one device will work independently from the others. That's basically the lab. Let me know if you guys have any questions. Talk to you again soon.